Good morning, ma'am. Myself, Harris Prasanna from Department of Artificial Intelligence and Data Science. My case study is about application of subspaces. So let's move on to the topic. Moving to the table of contents, there are three parts. The first one is subspace, followed by properties, and the last one is applications. What is a subspace? In mathematics, and more specifically in linear algebra, a linear subspace, also known as a vector space, is a vector space that is a subset of some larger vector space. A linear subspace is usually simply called a subspace when the context serves to distinguish from other types of subspaces. Properties of subspaces. From the definition of vector spaces, it follows that subspaces are non-empty and are closed under sums and under scalar multiplies. Equivalently, subspaces can be characterized by the properties of being closed under linear combinations. That is, a non-empty set W is a subspace if and only if every linear combination of finitely many elements of W also belongs to W. The equivalent definition states that it is also equivalent to consider linear combinations of two elements at a time. In a topological vector space X, a subspace W need not to be topologically closed, but a finite dimensional subspace is always closed. The same is true for subspaces of finite dimension, that is, subspaces determined by a finite number of continuous linear functionals. Application of subspace. A geometric picture of linear transformations, which is what we use matrices to model, helps with these ideas. A linear transformation might use certain lines in a line. They simply map the line to the same line within a scaling vector. Any vector on such line is an eigenvector, and the scale factor by which the line is magnified as such is the eigenvalue. A linear transformation might, even when given any vector in 3D, only spit out vectors on a certain planar line. The set of vectors spat out in this way is the image of transformation, and you should see that the dimensionality of the image is clear from its geometric dimension. If the image is a plane, then the image has dimension 2 and so on. An example. Among many of the usefulness of the concept of subspaces is that it is itself a vector space. Hence, once a vector space has been built, one can construct many more examples by considering its vector space. I would say that the root of the fact that subspaces are important have to do a lot with linear transformations. It is not hard to show that the subspaces on the image of a linear transformation are vector spaces. Since these two things in larger part form the basis of most of linear algebra, to some degree, being able to know that you need not to consider anything wild or different when a linear transformation is not injective or surjective is a useful thing. Thank you.